Hello and welcome to lecture 10 of module 2 of this course on accelerator physics. Today we'll learn about transverse dynamics of beams with space charge. But before that, let's just quickly revise what we learned in the previous lecture. So we studied that the quadrupoles of reverse polarities are used in pairs for focusing the beam, because we have seen that quadrupoles focus in one direction and defocus in the other direction. So they are used in pairs for focusing the beam. Different types of focusing lattices like FODO, FOFODODO, solenoids, etc. These are used for focusing the beam in linacs. So yesterday we saw that inside the drift tube linac there are drift tubes, and in these drift tubes quadrupole magnets are put for focusing the beam. They could be arranged in any configuration like FODO, FOFODODO, or even a FOFOFO-DO-DO-DO configuration. For a periodic focusing system, the general equation of any particle is an ellipse. So we derived this in the previous lecture. At a given location S in trace space XX prime, each particle will lie on the ellipse defined by the twist parameters alpha, beta and gamma. The twist parameters are the same for all parameters, that is, ellipses for all the particles are concentric. So alpha, beta, gamma tell you about the shape and orientation of the ellipse. They tell you about the beam properties, the beam size, the beam divergence, whether the beam is diverging or converging, and so on. The area of each ellipse depends upon the value of the constant of motion, which is epsilon I for that particle. The outermost ellipse defines the maximum beam size and the maximum beam divergence. The beam emittance is defined as the area of the outermost ellipse divided by pi. We also saw that the single particle behavior can be studied by solving the Hill's equation, which is a single particle equation. So it includes the force due to the quadrupole magnet, or whatever the case may be, whatever element is there. We can also study the single particle behavior by the transfer matrix method. So if we know the transfer matrix of the element and we know the initial coordinates of the particle before the elements, then we can find out the final coordinates of the particle at the end of that element. The behavior of the beam envelope can be studied by solving the envelope equation, which we derived in the previous lecture, or by sigma matrix method. So sigma matrices are basically in terms of the twist parameters alpha, beta and gamma. So they give you the entire information about the beam at a particular location. So if you know the sigma matrix at the initial location and you know the transfer matrix for the element in between, you can find out the final sigma matrix and hence the beam size, beam divergence at the end of that element. Now in all this analysis, we have studied the effect of only external elements like quadrupoles, etc. on the beam. We have not studied the effect of the force due to the beam itself. So if the beam is a high current beam, so there will be many particles of the same charge in the beam, and these particles being of the same charge will tend to repel each other, because of which there will be a repulsive force acting on the particles due to the beam itself. So this is known as the space charge force, and today we will study about the transverse beam dynamics including the space charge forces. So this is particularly important for high intensity beams, and high intensity beams are required for several applications. One is the accelerator driven system. So I discussed about this in the first lecture. So we need a high current beam here. Another application is spallation neutron sources. Here also a high intensity beam hits a target and spallation neutrons are produced, which are used for doing experiments. So in order to have a high yield of neutron, we should have a high current proton beam. So both of these applications require very high intensity beams. So high intensity beams are high current beams, and since the beam current is high and particles in the beam are of the same charge, they will experience Coulombic repulsion. This results in degradation of the beam quality, so the beam emittance will increase in beam size resulting in beam loss. So since these forces are repulsive, the beam size tends to increase, and if the beam hits the aperture, beam will be lost. Beam loss at high energies can result in activation of the accelerating structures, preventing hands-on maintenance of the accelerator. Now, if beam is lost at higher energies, this can activate the structure, so that during operation, nobody is allowed to enter the the accelerator tunnel. But after the accelerator is shut down, people enter inside to for maintaining the structure. So if there is beam loss at higher energies, this can activate the accelerating structure so that it can become radioactive. And even after the beam is shut down, the accelerator is shut down, people will not be able to enter inside for hands-on maintenance of the structure. So beam loss at higher energies is undesirable. So the force due to the beam self-charge is known as space charge force. Now, in order to understand the space charge force in high intensity beams, let us consider a very simple model. Let us consider a cylindrical uniform beam. So let's say we have a cylindrical uniform beam with circular cross section. The beam current here is I, the beam radius is A, and the beam is moving with a velocity V. So due to symmetry, the electric field here will be in the radial direction. So we will have an electric field which is in the radial direction and a magnetic field which is in the azimuthal direction. So there will be only two components of electric field and magnetic field. Here rho is the charge density and J is the current density. So the electric field, the radial component of electric field can be calculated. So we know that from Maxwell's equation, divergence of E is equal to rho by epsilon 0. Applying Gauss's law, we can write the volume integral of divergence of E is equal to the surface integral of E dot ds. So applying this over a cylinder of radius r and length L, we get this expression. And by simplifying this further, we get the radial component of electric field as this expression. So we see that it depends upon the beam current. Higher the beam current, higher is the radial component of electric field. It depends upon R, the distance from the center, and also on the beam size. Similarly, we can calculate the magnetic field due to this cylindrical uniform beam with circular cross section. So there will be only theta component of magnetic field. So again, using Maxwell's equation, curl of B is equal to mu 0 J, and applying the Stokes theorem, we can write B R d theta is equal to integral of this is equal to curl of B dot dA. So applying this over a cross section of radius R, we get b theta 2 pi r is equal to mu 0 r square pi beta c rho. Again simplifying this, we get b theta is equal to I by 2 pi epsilon 0 c square r by a square. Now force acting on a charged particle due to this uniform cylinder. So we can calculate using Lorentz force. So the force in the radial direction will be QER minus VZ into B theta. So we have already calculated the ER and B theta values. If we substitute in the Lorentz force, we get this expression. So, and if we simplify this, we get this expression for the force acting on any charged particle due to this uniform cylindrical charge of uniform cross section. So here we see that there are two components to this force. One is due to the electric field, the other is due to the magnetic field. The component of force due to the electric field is repulsive, and due to the magnetic field is attractive. You can see here because there is a minus sign here. So it is attractive, whereas the component due to the electric field is repulsive. So we can also see that the force is linear in R. So the force is linear in R, and the Coulomb effects in linacs are most important in non-relativistic beam at low velocities. So as the beam becomes relativistic and beta approaches 1, so the magnetic field, the force due to the magnetic field will cancel the Coulombic repulsion due to the electric field. So the Coulomb effects or the space charge effects are more important at lower energies for high current beams. For relativistic beam, the self-magnetic forces increase and produce partial cancellation of the electric Coulomb forces. So, at higher energies, or let's say for electrons, because we know for electrons the beam becomes relativistic at lower values of kinetic energy, the space charge forces are not so important. They are more important for high current beams, ion beams at lower energies. So moving charges here, they produce mutually repulsive electric field and attractive magnetic field. Now we have calculated for a uniform charge distribution. Now if we calculate for a non-uniform charge distribution, let's consider a Gaussian beam distribution for a circular cross section. So the charge density is given by this expression. So again, using Maxwell's equation, so divergence of E is equal to rho by epsilon 0. Now rho, we substitute the distribution, the Gaussian distribution here, and we can calculate the force in the radial direction using QER by gamma square as we have calculated previously. So we get this expression. Now here notice that for a non-uniform Gaussian beam, the space charge radial force is no longer radial in R. So this is a non-linear force now. So the force depends upon the distribution, the type of distribution. For a uniform charge distribution, it is linear. For a non-uniform distribution, like a Gaussian distribution, it is non-linear. So this is a uniformly distributed beam in real space in X and Y. So this is X and this is Y. And here we see that the force is linear in R. This is a Gaussian distributed beam, so that the charge density is high at the center and falling as the radius increases. So for a Gaussian distributed beam, the force is non-linear. So we can summarize the result here. The Coulomb effects in linacs are usually most important in non-relativistic beams at low velocities, because for relativistic beams, the self-magnetic forces increase and produce partial cancellation of the Coulombic forces. So they are important at lower energies only. The net effect of the Coulomb interaction in a multi-particle system can be separated into two contributions. So one is the space charge field, the result of combining the fields from all the particles to produce a smoothed field distribution, which varies appreciably over distances that are large compared with the average separation of the particles. So this is what we have just calculated, the effect of the entire charge distribution on a single particle. Then the second is the contribution arising from the particulate nature of the beam, which include short range fields describing binary small impact Coulomb collision. So between adjacent particles there are Coulombic collisions. So these are short range forces. So typically the particles in the Linac bunch exceed 10 to the power of 8 particles. There are large number of particles in a bunch, and the effect of the collisions are very small as compared to the effects of average space charge field. So we usually consider the force on the charge particle due to the entire beam distribution. The force due to the Coulombic repulsion of adjacent particles, this is short range and usually very small and can be ignored. Now let's see how the beam can be described. Every particle in the beam can be described by 3 position and 3 momentum coordinates. So we usually talk of the beam in phase space. So each particle can be described by 3 position and 3 momentum coordinates. Then each particle is represented by a single point in the 6-dimensional phase space of coordinates and momenta. In practice, it is convenient to work with two-dimensional phase space projection. So even though we are describing the beam in six-dimensional phase space, so we take projections in two-dimensional phase spaces and we work with them. So the normalized phase space projections are x and px by mc, y and py by mc, z and pz by mc. So x, y, z are the coordinates and px, py and pz are the momentum components. Now instead of transverse momenta, it is convenient to measure the divergence angle. So we have already seen in the previous lectures that it is convenient to work in trace space x and x prime rather than x and px. So we take the divergence angle dx by ds, which is same thing as x prime, dy by ds, which is same thing as y prime. So plots of x prime and x prime and y prime are known as trace space or unnormalized phase space projection. So you can see here, this is the projection in x prime. This is a projection of the beam in y prime. This is in real space x and y. And this is in the z direction in terms of phase and energy. So in longitudinal phase space, position and momentum relative to the synchronous particle can be used. But more often these are replaced by phase and energy phi and w. So you can see here this in z direction, instead of z prime, we have used phase and energy, and this is with respect to the synchronous particle. The beam phase space contours in a linac have the approximate shape of an ellipse. So we have derived this in the previous lecture. We saw that whenever there are linear forces, the beam or any charged particle in phase space travels in a elliptical path. So this is due to the predominance of linear focusing forces, quadrupoles. The focusing force due to a quadrupole is linear in most accelerators. With linear focusing, the trajectory of each particle in phase space lies on an ellipse, which is called the trajectory ellipse. So these are the trajectory ellipse for various particles. So each particle has the same twist parameters alpha, beta and gamma. What differs is the value of the constant of motion, which is epsilon I. Due to the tendency of linac beams to exhibit approximately elliptical phase space distributions, it is conventional to define for each two-dimensional projection a quantity called emittance, which is proportional to the area of the chosen beam ellipse. So we define an emittance. So we saw in the previous lecture that the outermost area of the outermost ellipse divided by pi is known as the emittance. So just quickly revising what we have already done, the beam phase space contours in a linac have the approximate shape of an ellipse. The general equation of the ellipse is given by gamma x square plus 2 alpha x prime plus beta x prime square is equal to epsilon. So here alpha, beta, gamma are the twist parameters and they are related as gamma is equal to 1 plus alpha square by beta. So these twist parameters tell you about the shape and orientation of the ellipse. They also tell you about the beam properties. So the maximum beam size is given by under root beta epsilon. This is the maximum beam size. This is the beam half width. Similarly, the maximum beam divergence xm prime is equal to under root gamma epsilon. So this is this value. It is the beam half divergence. So the motion of the particles is along constant Hamiltonian. And then emittance is defined as the area of the outermost ellipse divided by pi. So here emittance corresponds, it corresponds to the constant of motion of the outermost particle. So quality of the beam is quantitatively described by its emittance. So emittance is a figure of merit of the beam, which is closely related to the area of the two-dimensional projections of the hyperellipsoidal volume occupied by the particles in six-dimensional phase space on xpx, ypy and zpz plane. So the beam occupies a hyperellipsoid in the six-dimensional phase space xpx, ypy, zpz. So we take projection and emittance is defined for the projection. in two-dimensional phase spaces. The transverse emittance is normally expressed in millimeter millirad, since x prime and y prime are preferred to px and py. So we normally use, instead of the phase space, the trace space. So the emittance is taken in the trace space x prime. So the units are millimeter millirad. The longitudinal emittance defined only for bunched beams. So if it is a DC beam, if the beam is not bunched, then the beam is continuous in the z direction. So the emittance is not defined in the z direction. The longitudinal emittance is defined only for bunched beams. This is normally expressed in nanosecond keV or degree keV. In many cases, an ellipse can roughly approximate the emittance boundary. Sometimes beams do not have proper elliptical boundaries. So the area of such an ellipse represents the full emittance of the beam in that plane, and its size is determined by the outermost particle of the distribution. So whenever there are linear forces, the trajectories of the particles in phase space, they lie on an ellipse. But if there are non-linear forces, the particles can lie outside the ellipse. So you can still use an ellipse to roughly approximate the emittance boundary. And then in this case, area of such an ellipse represents the full emittance of the beam in that plane, and its size is determined by the outermost particle of the distribution. But sometimes it can happen that let's say some very few particles can go far away from the main beam. So here, as you can see in this picture, so this is taken from a code called TraceFin. So you can see here most of the beam is in the central region, but a few particles have now are far away from the central core of the beam. So if non-linear forces are present, then projections of the phase space of a real beam may have complex shape and poorly defined boundary. A few particles may go very distant from the beam core and form halo. So this is what is known as the beam halo. So if you calculate the emittance, containing all the particles, this value will come out to be very large. So in such cases, the emittance can be defined as 1 by pi times the area delimited by an isodensity contour containing some large fraction of the particles. So you can define a 90% emittance or a 99% emittance. So you can define an ellipse which contains, let's say, 90% of the particles or 99% of the particles. So, so an ellipse which contains 90% of the particles, 99% of the particles, and that is called the 90% emittance or 99% emittance. So here you can see this, for this beam, this is the 50% ellipse. So the area of this ellipse will be the 50% emittance. This is the 90% ellipse. So containing the 90% of the particles in the beam, so this will be the 90% emittance. And this is the ellipse containing 99% of the particles, and this will correspond to the 99% emittance. So generally beams do not have well-defined boundaries. So in the presence of non-linear forces, the beam need not be an elliptical beam. So one method for assigning an emittance is to choose a specific density contour in phase space, such as at 50%, 90%, 99% of the maximum density. It can be shown that under certain conditions, such emittances are conserved. For example, when Liouville's theorem is satisfied in the 6-dimensional phase space, or when forces in the 3 orthogonal directions, that is x, y and z, they are uncoupled. Beam distributions. Now let us talk of beam distributions. We've already seen a uniform distribution and a Gaussian distribution. So beam of charged particles can be conveniently represented by means of a distribution function f of the charge in 4-dimensional phase space or 6-dimensional phase space. So 4-dimensional phase space, x px, y py is generally used when you have a DC beam. So you need not define the beam in the z direction. So in that case, a 4-dimensional phase space is sufficient to define the beam. When you have a bunched beam, in that case, 6-dimensional phase space is used, x px, y py and z pz. So motion of the particles can be described as that of a set of points in 6-dimensional phase space. So you can have a distribution function in 6-dimensional phase space, which can be defined like this, or in 4-dimensional phase space as like this: f is equal to f, which is a function of x px y py, and in this case for 6-dimensional phase space, x px y py z pz. So motion of the center of mass of the beam is described by first moment. So first moments are, you can take average over x prime, y prime of the particle distribution f x prime y prime, which is then defined statistically as, so average x average is taking the integral of x multiplied by the distribution function f, and taking the integral over dx prime dy prime. Here f is normalized to 1, and similarly for the other x prime average, y and y prime average. The other important information is contained in the second moment. So second moment is defined as average over x square, average over x prime, xy prime, and so on. So of the particle distributions, which is defined statistically in a similar way. So it is defined again just like we have defined the first moment. So average of x square is the taking the integral of x minus average x square multiplied by the distribution function f, and integrating over dx prime dy prime. Similarly, the second moment of x prime, it can be defined in this manner, and so on for the other 8. The root mean square values of such quantities are defined as xRMS is taken as, so you simply take the square root of the second moment and you can define the root mean square or the RMS of such quantities.